The National Electrical Code does not break down the specific method of grounding switches. Grounding of switches has been a requirement within the National Electrical Code since the 1920s. The National Electrical Code is updated every 3 years, and since the 1920s, the requirements for grounding switches have not significantly changed. The purpose of grounding electrical components, including switches, is to provide a lower impedance path for fault current to return to the source, which facilitates the rapid operation of overcurrent protective devices such as circuit breakers or fuses. This helps to minimize the risk of electrical shock and fire. Grounding ensures that any exposed metal parts of an electrical system are at or near ground potential. This reduces the risk of electric shock if a person comes into contact with a faulty device. The NEC provides comprehensive guidelines for grounding and bonding electrical systems, ensuring safety and proper function. Grounding and bonding create a low impedance path for fault current, allowing overcurrent protection devices to quickly trip and disconnect the circuit, preventing prolonged exposure to dangerous voltage levels. Grounding stabilizes voltage to earth during normal operation. Without a ground reference, voltage can fluctuate, causing equipment malfunction or damage. Grounding helps minimize electrical noise and interference, which can disrupt sensitive electronic equipment. Static electricity can build up on non-grounded objects, posing a risk of discharge and potential damage to electronic components. Grounding provides a path for static charges to dissipate safely. Firstly, the grounding electrode system typically includes a grounding electrode conductor connected to a grounding electrode, such as a ground rod, metal water pipe, or ground ring. Secondly, the equipment grounding conductor provides a path for fault current from electrical equipment back to the source. This conductor is typically a wire that runs with the circuit conductors. Thirdly, bonding involves connecting all non-current carrying metal parts of an electrical system together to create a common ground potential. This includes metal conduits, enclosures, and equipment frames. The size of grounding conductors is determined by the size of the circuit conductors. The NEC provides tables that specify the minimum size of grounding conductors based on the ampacity of the circuit. Grounding conductors must be properly identified, typically by being green or green with a yellow stripe. This ensures that they are easily distinguishable from other conductors. Grounding connections must be made using approved methods, such as listed connectors or exothermic welding. Improper grounding connections can compromise the effectiveness of the grounding system. Regular inspection and testing of grounding systems are essential to ensure their continued effectiveness. This includes verifying the integrity of grounding connections and measuring ground resistance. The National Electrical Code Section 250 covers the general requirements for grounding and bonding. This section provides detailed information on grounding electrode systems, equipment grounding conductors, and bonding requirements. Section 250.4 outlines the general requirements for grounding electrical systems, including the need to create a low impedance path for fault current. Section 250.24 covers grounding separately derived systems such as generators and transformers. This section specifies the requirements for grounding the neutral conductor of these systems. Section 250.50 provides requirements for grounding electrodes, including the types of electrodes that are permitted and their installation requirements. Section 250.118 lists the types of equipment grounding conductors that are permitted, including wire, cable, and metal raceways. Section 250.122 specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device. Section 300.3 covers the general requirements for wiring methods, including the requirement that all conductors of a circuit, including the equipment grounding conductor, must be installed together in the same raceway or cable. Section 314.4 covers the grounding requirements for outlet boxes and device boxes, including the requirement that boxes must be grounded and that devices mounted in boxes must be bonded to the box. Section 404.9 covers the grounding requirements for switches, including the requirement that switches must be grounded if they are accessible to unqualified persons. The NEC also includes requirements for grounding specific types of equipment, such as motors, transformers, and appliances. Firstly, motors must be grounded to ensure that any fault current will be safely conducted back to the source. This helps to prevent electrical shock and fire hazards. Secondly, transformers must be grounded to protect against voltage surges and to provide a stable reference point for the electrical system. Thirdly, appliances must be grounded to prevent electrical shock hazards. Many appliances have exposed metal parts that could become energized if a fault occurs. Grounding ensures that these parts are at ground potential, minimizing the risk of shock. Grounding systems should be inspected regularly to ensure that they are in good condition and that all connections are tight and corrosion-free. Ground resistance testing should be performed periodically to verify that the grounding system is effective. If any problems are found during inspection or testing, they should be corrected immediately. Improper grounding can lead to a variety of problems, including electrical shock, fire hazards, and equipment damage. It is essential to follow the NEC requirements for grounding to ensure the safety and reliability of electrical systems. Changes in the National Electrical Code pertaining to grounding are made every 3 years. These revisions may clarify existing requirements, address new technologies, or enhance safety measures. These changes are typically proposed by industry experts, reviewed by code-making panels, and then subject to public comment before being incorporated into the updated code. Staying current with these changes is crucial for electrical professionals to ensure compliance and maintain the highest standards of safety. The National Electrical Code is not law unless adopted by a local jurisdiction. Therefore, it is important to check with the local authority having jurisdiction to determine which edition of the NEC is in effect. The AHJ may also have additional requirements that are not covered by the NEC. Compliance with the National Electrical Code is essential for ensuring the safety of electrical installations. Failure to comply with the NEC can result in fines, penalties, and even legal action. Firstly, proper grounding helps to prevent electrical shock, which can be fatal. Secondly, proper grounding helps to prevent fires, which can cause significant property damage and injuries. Thirdly, proper grounding helps to protect equipment from damage caused by voltage surges and other electrical disturbances. The grounding electrode system should consist of a metal underground water pipe, a ground ring, or ground rods. The metal underground water pipe should be in direct contact with the earth for at least 10 feet. The ground ring should be buried at least 30 inches below the surface of the earth and should encircle the building or structure. Ground rods should be driven into the earth at least 8 feet apart. Equipment grounding conductors are used to connect the non-current carrying metal parts of equipment to the grounding electrode system. These conductors provide a path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and clear the fault. Equipment grounding conductors must be sized according to the size of the circuit conductors. Bonding is the process of connecting all non-current carrying metal parts of a building or structure together to create a common ground potential. This helps to prevent voltage differences from developing between different parts of the building, which could create a shock hazard. Bonding conductors must be sized according to the size of the circuit conductors. Ground fault circuit interrupters, GFCIs, are devices that are designed to protect people from electrical shock. GFCIs work by monitoring the current flowing in a circuit. If the current flowing out of the circuit is different from the current flowing back into the circuit, the GFCI will trip and shut off the power to the circuit. GFCIs are required in many areas of the home, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, AFCIs, are devices that are designed to protect people from fires. AFCIs work by monitoring the current flowing in a circuit. If the current flowing in the circuit is abnormal, the AFCI will trip and shut off the power to the circuit. AFCIs are required in many areas of the home, such as bedrooms and living rooms. Surge protective devices, SPDs, are devices that are designed to protect equipment from damage caused by voltage surges. SPD work by diverting the surge current away from the equipment and back to the source. SPD are recommended for all electrical systems, especially those that are used to power sensitive electronic equipment. Electrical systems should be inspected regularly by a qualified electrician. During an inspection, the electrician will check the wiring, grounding, and other components of the electrical system to ensure that they are in good condition and that they meet all applicable codes and standards. Any problems that are found during the inspection should be corrected immediately. The use of proper grounding techniques is essential for ensuring the safety and reliability of electrical systems. By following the NEC requirements for grounding, you can help to prevent electrical shock, fires, and equipment damage. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician before performing any electrical work. Local codes and regulations may vary, so it is important to check with your local authority having jurisdiction to ensure compliance. The NEC is updated every 3 years to reflect changes in technology and safety practices. Staying current with the latest edition of the NEC is essential for electrical professionals. There are many resources available to help you learn more about grounding and bonding, including the NEC textbooks and online training courses. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the NEC requirements and best practices, you can help to ensure the safety of yourself, your family, and your property. Understanding the principles of grounding is crucial for anyone working with electrical systems. It is important to know how grounding works, why it is necessary, and how to properly install and maintain grounding systems. A well-designed and properly installed grounding system is a critical component of any electrical installation. It protects people from electrical shock, prevents fires, and protects equipment from damage. The cost of a grounding system is relatively low compared to the potential consequences of a faulty or non-existent grounding system. Investing in a good grounding system is a wise decision that can provide years of safe and reliable electrical service. Electrical safety is everyone's responsibility. By following the NEC requirements and best practices for grounding, you can help to create a safer environment for yourself and others. The grounding of switches has been a long-standing requirement in the electrical industry, driven by the need to protect individuals from electrical hazards. The history of grounding practices reflects a continuous effort to improve safety standards and adapt to evolving electrical technologies. While the fundamental principles of grounding remain consistent, specific requirements and methods may be refined over time to enhance their effectiveness. Consulting the latest edition of the NEC and seeking guidance from qualified electrical professionals are essential steps in ensuring that electrical installations meet current safety standards. In addition to the NEC, other standards and guidelines may provide further information on grounding practices. These resources can offer valuable insights into specific applications and techniques. Staying informed about the latest developments in grounding technology and practices is crucial for electrical professionals. Continuous learning and professional development help ensure that they are equipped to handle the challenges of modern electrical systems. Grounding is not a one-size-fits-all solution. The specific requirements for grounding may vary depending on the type of electrical system, the environment in which it is installed, and the applicable codes and regulations. A thorough understanding of these factors is essential for designing and installing an effective grounding system. Regular inspections and maintenance are crucial for ensuring the continued effectiveness of grounding systems. Over time, grounding connections can corrode or become loose, which can compromise their ability to provide a safe path for fault current. Periodic testing can help identify potential problems before they lead to electrical hazards. Grounding is an essential part of a comprehensive electrical safety program. It should be combined with other safety measures such as the use of personal protective equipment, lockout/tagout procedures, and regular safety training. A proactive approach to electrical safety can help prevent accidents and injuries. Electrical work can be dangerous, and it is important to take precautions to protect yourself from electrical hazards. Always de-energize circuits before working on them, use insulated tools, and wear appropriate personal protective equipment. If you are not qualified to perform electrical work, hire a qualified electrician. The National Electrical Code provides a comprehensive set of rules and guidelines for electrical installations. However, it is not a substitute for good judgment and common sense. Always use your best judgment when working with electrical systems, and if you are unsure about something, consult with a qualified electrician. Electrical safety is a shared responsibility. By following the NEC requirements and best practices, we can all help to create a safer environment for ourselves and others. The ongoing development and refinement of grounding practices reflect commitment to continuous improvement in electrical safety. By staying informed and embracing new technologies, we can further reduce the risk of electrical hazards. Grounding is a critical aspect of electrical engineering and should be given the attention it deserves. A thorough understanding of grounding principles and practices is essential for all electrical engineers. The NEC serves as a valuable resource for electrical engineers, providing guidance on the design, installation, and maintenance of electrical systems. However, electrical engineers should also be familiar with other relevant standards and guidelines. Continuous learning and professional development are essential for electrical engineers to stay current with the latest technologies and practices. The field of electrical engineering is constantly evolving, and it is important to keep up with the latest advancements. Grounding is a fundamental concept in electrical engineering and should be thoroughly understood by all electrical engineers. A solid understanding of grounding principles is essential for designing safe and reliable electrical systems. The NEC is a valuable tool for electrical engineers, but it should be used in conjunction with good engineering judgment and common sense. Electrical engineering is a challenging but rewarding profession. By staying informed, embracing new technologies, and using good judgment, electrical engineers can make a significant contribution to society.